algorithms rely on existing connections to make sense of data. But here, we begin with zero structure, a chaotic field of identical points. In the taxonomy of our 50 essential algorithms, this sits in the unsupervised machine learning category. This is algorithm number 18, k-means clustering. This is the starting state of an unsupervised problem. You are handed raw data points with no labels and no human guidance. Looking at this void, how does a machine deduce if there are 2 groups here or 3? Where do the boundaries fall? Because there is no teacher to provide a ground truth answer, the algorithm must deduce reality by measuring the physical distances between the points themselves. The math behind this was developed inside a telephone company in 1957. Stuart Lloyd, an engineer at Bell Labs, was working to compress continuous analog voice signals into discrete digital pulses. The objective of k-means is to partition that chaos into tight, separated groups. It uses a specific metric called the within-cluster sum of squared distances. By minimizing this physical distance, the algorithm ensures the tightest possible groupings. We can see the efficacy of this by running it on the famous iris dataset. On the left, k-means groups the data by geometry. On the right, we see the actual human-verified species labels. The math almost perfectly matches biological reality. K-means translates the subjective human task of categorization into a rigidly solvable geometric optimization problem. To understand the mechanics, look at the name. The K is the exact number of clusters you want to find. Means refers to the mathematical averages that act as the center of gravity for each of those clusters. The engine running this algorithm is Lloyd's loop. Drop centers, assign points, move centers to the average, and repeat until stable. Step 1 is initialization. The algorithm drops your requested k-centroids randomly into the space. Step 2 is the assignment phase. Every data point computes its precise Euclidean distance to every centroid, snapping allegiance to the closest one, inheriting its identity. This first pass creates a map, but because the initial centroids were dropped at random, the current groupings are just a guess. The system must now correct itself. Step 3 is the update phase. The centroid abandons its random starting position and slides directly to the spatial center of its newly acquired points. This new coordinate is found by calculating the exact average of their x and y coordinates. Now the loop folds back on itself. Centroid movements change the distances, forcing edge points to reassign. That shifts the average, moving the centroids again. This cycle continues until convergence. It terminates when no points swap allegiance, locking the centroids into optimal positions. Beyond the individual points, the algorithm carves hard geometric boundaries through the entire dimension. Through iterative looping, the system self-corrects from randomness into a mathematically optimized structure. The result is a clear structure. An unlabeled dataset is partitioned using averages and geometric distance, but the algorithm cannot discover the value of k on its own. A human user must predetermine how many clusters to look for, often by plotting the drop-off in error to find the visual elbow. Beyond that manual requirement, the assignment step carries a significant mathematical cost. The algorithm explicitly compares every single data point to every centroid, and it repeats this on every pass. This cost scales aggressively. For 10,000 points and 3 clusters, the machine performs 30,000 distance checks per iteration. It is an artifact of 1950s engineering logic, but its application to modern, massive datasets creates a large computational footprint. So how is this brute force geometry actually written in code, and what programmatic strategies are required to manage this mathematical cost? Group thousands of points, code has to calculate distances over and over. In a single pass, the algorithm compares every single data point, n, to every target center, k, across every dimension, d. Multiply those together, and the computational cost scales up rapidly. And that is exactly one pass. To find the final clusters, it multiplies that entire web of math by I, the total number of iterations needed for the centers to stop moving. The saving grace here is that the cost scales linearly with the number of data points. If you double the size of your dataset, the math only doubles, making it possible to process millions of rows without crashing the system. This diagram outlines the complexity constraints of k-means clustering. Look at the warning under the cost section. Finding the absolute perfect global optimum for these clusters is mathematically NP hard, meaning it's impossible to solve perfectly on a large scale. Because of that mathematical limit, the algorithm settles. It loops until it finds a local optimum, a good enough answer. This makes the final clusters highly vulnerable to wherever the starting points randomly landed. The raw geometry is fast, but it's imprecise by nature. The actual Python code we write must explicitly defend against this mathematical weakness. In modern machine learning, we don't write geometric calculations from scratch. We use libraries like scikit-learn as a black box, hiding the heavy math. To execute the entire clustering process, it only takes 6 lines of Python. It starts with the initialization. The n-clusters parameter is the k-value. The algorithm cannot figure out how many groups exist on its own, so the programmer is forced to guess or provide that number up front. Next is the init parameter, set to k-means++. This is the defense against the local optimum trap. Instead of dropping the starting centers completely at random, this forces them to spread out evenly across the data. Then we have a brute force safety net, n-init equals 10. This tells the code to silently run the entire clustering process 10 separate times from different starting positions, returning only the single best result. The actual execution is triggered by the .fit command. We pass in our raw feature matrix, x. Notice there are 0 labels provided here. The algorithm is flying blind. Once it finishes, we extract the results. Calling labels underscore spits out an array containing the final cluster ID assignment for every individual data point. We also pull cluster centers underscore, revealing the precise geometric coordinates of where the center of each group finally rested. This concise syntax functions as a highly optimized protective wrapper, taming a volatile geometric problem with just a few characters. This diagram shows Lloyd's algorithm, the raw mechanical loop operating underneath that .fit abstraction. In panel 2, we see the heaviest computational step. The algorithm physically calculates the distance from every single point to every available centroid. Based on those distances, it mathematically links each point to its closest centroid. In raw Python code, this assignment is executed using an argmin function to pick the shortest path. Then it moves to the update phase. A mean function averages the coordinates of a cluster's members. The centroid then slides precisely to that new center of gravity. That loop repeats, acting as its own braking system. Checks like np.allClose monitor the movement of the centroids, halting execution the moment they stop shifting. You can pull the textbook implementation straight from this GitHub repository to see the process written out from scratch. Understanding this raw mechanical loop is the only way you truly grasp the computational bill you pay when you type .fit. While the sklearn code we just saw is elegantly short, its strict geometric assumptions hide some very sharp operational edges in practice. This diagram highlights the algorithm's shape prejudice. Because it measures distance radially in all directions, it assumes all clusters are perfectly round. If you feed it crescent or arbitrary shapes, it fails completely. It is also highly vulnerable to outliers. Because the update step relies entirely on a mathematical mean, a single extreme data point placed far outside the group will violently drag the centroid away from the true cluster, and it remains blind to the natural shape of the data. If the true structure has 5 groups, but you pass n-clusters equals 3, the code will happily force the data into 3 incorrect bins. Knowing these flaws, we have to ask, when does this shape-biased, outlier-sensitive algorithm actually succeed beautifully in production? And when does it quietly corrupt a data pipeline? Off track. Given these sharp mathematical edges, why does k-means clustering remain the undisputed default algorithm in production environments? You see its true commercial value in customer and market segmentation. Companies take millions of unique, chaotic shopper histories and use k-means to boil them down into 3 or 4 actionable behavioral profiles. You can actually see this compression power at work in image color quantization. Take a vibrant image of an aurora borealis and ask the algorithm to reconstruct it using only a few distinct colors. Every individual pixel is snapped to its nearest centroid. The underlying data complexity drops drastically. That same logic is deployed everywhere. It organizes massive document libraries, it isolates network anomalies by flagging data points that sit too far from any recognized centroid. It acts as a high-speed preprocessor, structuring raw data before passing it to heavier machine learning pipelines. At its core, K-means is an engine for abstraction. When you can replace the sprawling chaos of reality with a few representative centers, massive systems run with incredible efficiency. Looking at this performance breakdown, you can see exactly why engineers stick with it. The algorithm is brutally simple, and the time complexity is linear, O of n times k times d. That guarantees blinding speed and predictable scaling, even on massive datasets. It is also mechanically reliable. Because each iteration mathematically reduces the total squared distance, it is guaranteed to converge on a solution. The output is equally clear. Every cluster gets exactly one centroid, and every data point gets exactly one hard label. There are no fuzzy probabilities or overlapping boundaries to explain to your stakeholders. Give this algorithm its perfect environment. Data that naturally forms well-separated, roughly spherical clusters of similar size, and it performs flawlessly. When your data cooperates with those geometry requirements, trading advanced algorithmic complexity for raw speed and predictability is always the correct engineering choice. But look at this graphic highlighting the algorithm's limits. This is the shape problem. K-means relies entirely on abstract centers, so it fails completely on non-circular data, like nested rings or crescents. When you face complex shapes, the practitioner's fix is to abandon K-means entirely. You swap to density-based algorithms, like DBS scan, or Gaussian mixture models, which can map to irregular contours. Then there is the outlier problem. Because the centroid is calculated as an average, a single extreme anomaly will drag the center of mass far away from the true grouping. There are two immediate workarounds for this. You either aggressively filter anomalies out of your dataset before running the algorithm, or you switch to K-metoids, which anchors the cluster to an actual physical data point rather than an abstract mean. This chart illustrates the unknown K-trap. The algorithm cannot detect how many clusters exist. Arbitrary guessing forces false groupings. To find the optimum, run the elbow method, locating the exact joint where within cluster distance flattens. Or avoid K entirely by using hierarchical clustering. And before you run a single line of code, follow the universal golden rule. Always scale and normalize your features. If you skip this, massive numerical ranges will silently swallow your underlying cluster structure. Successful deployment comes down to a defensive mindset. You have to know the exact geometric assumptions the algorithm makes and intervene the moment reality diverges. So here is your final decision matrix. If your data is scaled, well-separated, and roughly spherical, K-means is fast and unbeatable. If your data has weird shapes, heavy outliers, or an unknown number of natural groups, reach for your alternative toolkit. This breakdown covers algorithm number 18 from Imran Ahmad's book, 50 Algorithms Every Programmer Should Know. You can find the link to the book on Amazon, the runnable Python code on GitHub, and more resources at neuralsca. It started in the 1950s as a signal compression trick inside a Bell Labs memo. Today, that simple loop of magnets and crowds remains the absolute default method for finding structure in an unlabeled world.